Let's first start with this announcement. I don't know if any of you are interested, but it's worth thinking about, and you might know of someone who may be interested. Okay? There's a program that the National Science Foundation sponsors called the Norris Scholars Program. Okay? And what this is primarily a way to try to attract more people interested in teaching high school math and science. Here in Alabama, we're woefully, I think across the country, woefully short in good qualified math and science teachers. Okay? And so it's a program designed to help remedy that. And there was one at UAB, but I think it's run out now. They're like 3 to 5 year grants. I believe they're gone. University of Alabama had one. If it's not gone, it's awfully close to being in it. Alabama A&M has recently gotten an award for a North Scholars Program. Now theirs is a little different from the other two, and you'll have to go and read the information. But if any of you are or know of anyone interested in teaching math or science at the high school level, they will basically, I believe, pay just about all of your last 2 years of college. I mean, that's what the program does. So if you are or know of someone who's interested in teaching, a lot more information is here. How can you find out about it? Check your emails, because this went to you as well as it went to me. Okay, so check your emails. And find out more about it. There's a link. Go to it and see what's up with it. All right. Now let's talk about how today's going to go, we hope, or it looks like. We're going to start with Chapter 19. We have made great progress in 19, so I believe probably in the next 2 hours we'll easily finish Chapter 19. That means we'll turn around and start Chapter 20, okay? Now, at 3:15, we will stop wherever we are in 20, I assume it'll be, and then we'll do the lab that was scheduled that sort of goes along with 19, okay? And I think I told you before, it's a very short lab, okay? There are only 10 questions, 10 possible points you can get off the lab part. We'll do them as a group, and we'll get those done. And then the second part of the lab is answering questions, okay? At the end of Chapter 18, there were 16 questions for thought and 4 questions for further analysis. Total of 20 questions. Answer any 15 or more of those 20 questions. Write the answers down on a separate piece of paper. And you don't have to write the questions if you want to just put let's see, questions for thought, QFT number 3, or FFA number 4, or whatever, then, just write those answers down. That can be done in a sentence or 2 each, I think. Maybe a couple of them might require 3 sentences or something like that. But they're pretty quick and easy to do. A great idea to get those done before you take the test for the last 30 minutes today, because that will be a great way to study Chapter 18. Is to answer those questions. And you got to do it for lab anyway, so why not, if you're into killing birds, kill 2 birds with 1 stone, okay? Get it done, okay? So, that's, will last 30 minutes. We'll be taking the test on Chapter 18. So let's look ahead. Thursday, since we will have finished 19 today, we will have the lab for 19 on Thursday, and we'll also have the test for 19 on Thursday. So we'll have 2 hours, and 30 minutes again on Thursday. Only we'll be doing with 19 like we were doing for 18 today. Or 19 and 18 we'll do 19 and 20 next time. Okay. All right. Any questions on how we're going to proceed? Okay. Then what we're doing here, and this is where we left off last time, is locating and measuring earthquakes. Okay, the first, yes.
So, which questions was it that you said? You said they're applying the concepts?
Yeah, not applying concepts. Next page. 15 or more. What if you get a question wrong? Okay? So if you do more than 15, if you get 15 correct answers, you get 15 points. Okay? So if you get some wrong answers, I want you to be able to get all 15 points. So do a few extras just to make sure you get all your points that you can. Because the rest of the lab is only going to be 10 points worth. So the other 15 points come from those questions. All right. Any questions on that? All right. So we've been talking about earthquakes. We talked about what causes them, that type of stuff. So how do we locate, and even more importantly, well, both of them are important, earthquakes. Before we get into that, let's get a little bit of a couple of definitions down. The focus of an earthquake is actually where it occurred, usually deep into the Earth's crust or mantle, somewhere down there, pretty deep. Some have been shallow, but most of them pretty deep. And that's the actual origin of the seismic waves. Okay? That's the focus. You never hear people talk about the focus of the earthquake. They talk about the epicenter of the earthquake. And if what I was just describing you thought was the epicenter, no, it isn't. The epicenter is then, if that earthquake is several miles down here, where it actually happened, that's the focus. The epicenter is the surface of the earth where that occurred, directly above where that occurred. That's called the epicenter. The location on the earth's surface directly above the focus. The focus could have been shallow, or it could have been way, way, way deep. All right. So with those two definitions in mind, let's then move to what a seismograph is. Graph means to measure. Okay? So this is something that measures seismic activity. I didn't think of how you say the word. Seismic activity. Okay? It's an instrument used to detect and measure earthquakes. Now, let's see if there's a picture. I think there. No. Okay. Oh, this is a picture of the focus. Let's say that we had a tensional forces going on here. Tensional stresses. Stress is tension. Okay. Tensional stress here. And so you had this part under here is called the. Here they have the fault plane, right? Okay, that's this area here where the break has occurred. It's the fault plane. What is the underside of that fault plane called? The foot wall. I can't lift it any more time, okay? The foot wall, the upper part is called the hanging wall. Now, how I knew this was a tensional stress is because the hanging wall slid down the foot wall. Or it would have, but it was hung up here on something. We don't know what. And when that gave way, that created the earthquake. Okay? Now, this is definitely not drawn to scale. Nowhere close. You don't have that kind of movement of earth at that shallow of a focus. So they're sort of making this up. Okay, but they're just doing it for illustrative purposes. What kind of fault would you call that? There were three kinds of fault we talked about. Normal fault, reverse fault, or thrust fault. Which one would this be? Normal. Normal fault. That's when the hanging wall slides down the foot wall. That's a normal fault. When the hanging wall pushes up the foot wall, that's a thrust fault. And when it's a very shallow angled thrust fault, that's a reverse fault. And when it's a very shallow reverse fault, that's a thrust fault. Okay, just a little bit of review for when this comes up. Okay, now, where that break occurred, whatever was holding that hanging wall there and keeping it from moving, when it finally broke or rebounded or whatever it did to create the vibrations, that place is called the focus, usually way deep. Okay? Directly above that, that's the epicenter of the earthquake. That's what our instruments measure. Where is the epicenter of the earthquake? Okay. Now, let's see if they have a picture of a seismograph. I think they do. Yes, here it is. It's an instrument that's really bolted down into the rock. I mean, into the body of the earth. It is fixed as part of that thing. It's not on shifting sand or anything like that. It is attached there. Now, it has a big, tall column here, and it detects motion back and forth this way. It has a heavy weight out here. This is a wire that suspends here. This is, you don't see it, but this is a freely moving joint here. Well lubricated, all that kind of stuff. You just can't see it. It's on the back side of that. When there is motion of the earth, the heavy weight tends, Newton's first law, tends to stay in place, and the rolling paper, and it just constantly is rolling, it will detect, and that would be your seismic waves. Okay? This is a revolving paper-covered drum that just is constantly measuring. And most of the time, absolutely nothing's going on. But when there is an earthquake, it'll measure. First waves to get there are which ones?
The S wave.
Okay. There's no F.
S.
S. No, that's secondary, meaning they get there
so
second.
The P wave.
P wave, primary means first. Prime, first. Primo. Okay, first. They get there first. They're the fastest waves, and they're longitudinal waves. What's another characteristic of P wave as it differs from an S wave? It's faster, primary. What's another difference between a P and an S wave? Yeah, it will travel through water. S waves will not. Why? Because a P wave is a longitudinal, another word for it, pressure wave, compressional wave. It'll travel through any medium, solid, liquid, or gas. Okay? S wave, shear wave, it can only move through a solid. A liquid will not support shear activity. Okay? Neither will a gas. But it'll only go through, the P wave will only go through, is the only wave that will go through liquids and gases. And then the third wave is your surface wave. Once it reaches the surface, then it creates another wave. Now it may look like the biggest of the waves, but it's actually the tertiary. It's the third to get there. It's the slowest of all. Of course, the other two waves have to get to the surface before the surface wave even is created. Okay? And it's up and down motion, sort of like a water wave. Okay? And moves out from there. All right. Now, here's the results. We just talked about it. The P waves travel faster than S waves. Primary waves get there first. Secondary waves get there second. Okay? Now, the difference in their arrival times correlates to the distance from the earthquake. Because the P waves are a little faster, okay, it would be like this, okay? Let's say that Thomas Earl's a speed demon, okay? He travels a mile per hour faster than I drive, okay? So he must be fast, okay, right? So, we leave from here and we go just down to the other building that's part of Lawson State here on the Bessemer campus. He's not going to beat me there by much, not at 1 mile per hour difference, right? But if we were driving from here to Tuscaloosa and he's going 1 mile per hour faster than me, he would get there quite a bit sooner than me, okay? If we were going from here to Atlanta and he's traveling 1 mile per hour faster than me, he'll get there much, much sooner than I will, right? Because 1 mile an hour isn't going to make any difference in a city block. It'll make some difference in adjacent towns. It'll make a big difference if you're traveling a long distance. So the difference in the arrival time correlates to how far they've traveled, the distance from the earthquake. Now, what they do, And I think I mentioned this before. We'll talk about another one. But there's two things that we're going to hit on both of this term, hopefully, of ways that the international community has worked together. There are very few ways the international community ever works together well. Okay, the two have been, and I'm not saying these are the only two, but two of them are seismography. In other words, the agreement to measure earthquakes. Every country in the world has seismographs set up at regular intervals in those countries. They're all tied to the same reporting system, and you get the data. Everybody gets the data from everybody else pretty close to real time. An outstanding agreement. Actually, science works together more than just about any other area. Sports works together pretty well. Medicine works together fairly well. Politicians don't work together very well, okay? So there's some places, things, well, the science side works together really well. The other thing that works together well are our tsunami warnings. These are set up all over the oceans surrounding all the countries, and they report quite well. So if there is a tsunami coming, they want everybody to know about it as soon as possible. So these two things, but the seismographs do. So what they do is when there is a seismic event, okay, an earthquake, then all the seismographs will record something, okay, and all of them are feeding the data back, and the ones closest to the earthquake are going to get the data first, and they are timed, okay? The ones further away, it'll be a little bit later, but they're all on the same time, chronometers, measuring time. And then further away is going to be a little in greater time before they get it. They send these data in real time, and then they calculate the differences in time correlating to the distance from the quake. So what they do, they get, let's just say the three, because we don't talk about triangulation here. They're actually going to get more than three. But the three closest seismographs to that earthquake are going to get their data in pretty fast because they're the ones that are going to get it first. And what they'll do, the first seismograph is this one at Z, and it gets the data pretty quickly, so you know the earthquake had to be somewhere on this circle of a 100-kilometer radius from point Z. This is the seismograph here. Just a short time later, Y gets the signal in, and they measure this and they compare. Now, I'm sorry, this isn't quite right. All of them are getting the data in. The difference is not the difference in these stations, but the difference between the S wave and the P wave. That's what I meant to be saying. Okay, the difference from the S wave and the P wave, they come in pretty close to each other at point Z, meaning you're only 100 kilometers from that epicenter. Okay? But then over here at station Y, the difference is such that you know you're 150 kilometers away. Well, now you know the epicenter is either here or there, but you don't know which. Both of these are 100 kilometers from Z and 150 kilometers from Y. When you get X's data in and you find out it was 200 kilometers because the difference in time between the P wave's arrival and the S wave arrival makes it such that you're 200 kilometers away, that puts you the epicenter right there. Not here or here, because those are the wrong distances from Z or from Y, but here it's 200 from X, 150 from Y, and 100 from Z. That's where the earthquake was. Okay? And they can do this fairly quickly. Now, these are awfully close distances. They can do these for thousands of miles, okay, and get that. So this is what they mean triangulation. They can't do it with two, they can't do it with one, they've got to have at least 3 reporting stations. More are fine. If they got more reporting stations in, they should all fall within a pretty close range there, okay? So, to pinpoint the epicenter of the focus. Here is a graph that sort of indicates this. Time of, it says first arrival of the P waves. They get there first, so the time is shorter. The S waves are there. If you're at this distance, you're close. You're close to that earthquake. Up here, if the time is this to this, you're a bit further away, so the distance from the earthquake. Time difference there, you're way out there. So this is how they determine how far this point is from the earthquake. It's the time difference between the P wave and the S wave. And they've got all these mapped out, calculated, so they know what they pretty much got to be. But you've got to have 3 points. Usually they'll have more. What is this very similar to? Something that I bet y'all use, maybe not every day, but you use periodically. Any of you use GPS? How does it know where you are? Okay, some satellites up there, but one satellite can't tell where you are. You need at least 3. Same deal. One's got a signal from you, another got a signal from you, another. With the 3 of them, they can pinpoint you. That's called triangulation. That's why they know exactly where you are, okay? Because of triangulation. If one of those 3 satellites were down and there wasn't another one in the area, it's not going to be able to do it, okay? They need 3 that are working. And like I said, usually there's well more than 3. And they can really pinpoint where you are. Same type deal as this. You don't have 2 signals there, you just have 1, but that'll still tell it to them. Okay. That's how they determine how far you are from a station. And by knowing that, then with 3 stations reporting, you can tell just about where the earthquake was. All right. Now, how do we classify earthquakes? There's a couple of different ways. The first of these is based on the depth of the focus. Remember, the focus is the point down there where it actually occurred, not the epicenter up here where the waves came to the surface. It's where it was down there. 3 ways they classify: shallow, intermediate, and deep focus earthquakes. Boy, look at these differences. The shallow focus earthquakes are down to 70 kilometers. That would be about 42 miles down. They call that shallow. 42 miles down. Okay? Now, about 85% of all earthquakes, okay, are in the shallow focus earthquake. The reason for that, the surface rocks are more brittle. There's more plate friction near the surface, and they're more likely to break abruptly. Okay, the deeper you get, the rocks are hotter, and they're more plastic, not as much elastic, so they're not going to have the major breaks. So that's why 80% of all earthquakes are in these shallow, only 42 miles deep. Goodness gracious, I can't even picture 1 mile down. You know, that would be incredibly deep to me, up to 42 miles. Then the intermediate focus earthquakes are from that 42 miles down to about 180 miles deep. Whoa! Okay? Now you're into the upper part of the mantle. Okay? These are all pretty much in the crust. Wait a minute. 42 miles, you're still in the crust, and yet we say that negligible mass of the Earth's surface. Wow. Earth is a big ball. Okay. But these intermediate focus quakes, you're into the upper part of the mantle from 42 miles down to about 180 miles. The deep focus earthquakes, the really deep ones. Now, there's something wrong here. I don't remember. I have to look it up every time. I think that's supposed to be 350 on both. And they have 300 on one and 350 on the other. 350. It's supposed to be 350. Okay. I'm not that picky on things, but it just seems like the typesetter should have been more careful. Let me get my pen set up. And I'll do dark blue because that looks like dark blue here. 350 kilometers, which would be more than 180, whatever that would be. Then the deep focus earthquakes from 350 kilometers, which would be, let's just say 200 miles. It won't be, that's not far. 200 miles deep to 420 miles deep. Yeah, okay. Now you're in the lower part of the upper mantle, okay? Wow, that's a weird way to say it. How do you know you're still in the upper mantle? All this plate activity is happening in the asthenosphere, which is from the upper mantle through the crust. There's no quaking going on underneath the asthenosphere. That's a rather fixed ball down there. You know, it's only above the asthenosphere that you have the plate movement. So in the lower part of the upper mantle, that goes down to about 420 miles deep. And you're still in the upper mantle. You're not even in the lower mantle yet. Now, about 3% of all earthquakes are deep focus earthquakes. Wow. How many would then be in the intermediate focus earthquakes? 85% are shallow, 3% are deep. Quick math. 85 and 3 is 88, subtract from 100%. 12%. About 12% of intermediate. So the vast majority are shallow focus earthquakes in the crust, okay? Intermediate focus earthquakes, the upper part of the upper mantle, and then the deep focus earthquakes are in the lower part, still of the upper mantle. Okay. So the mantle is really one thick piece of the earth. All right. So that's one way to classify earthquakes. Where did they originate? Shallow, intermediate, or deep? And deep is really, really deep. Intermediate is pretty deep to me. In fact, some of the shallows are awfully deep. Another way to measure earthquakes is measuring their strength. Okay? Now, early on, they measured it by how much damage they did. The structural damage to buildings, fires, landscapes, displacement of land surfaces, tsunamis or tidal waves that were created. That's how we measure. Well, not probably the best way. Because what if the earthquake happened in an area where there weren't many buildings, so there wouldn't be much damage to buildings? If there weren't many buildings, there probably aren't many gas lines to catch fires. Yeah, you could have some pretty major landslides, but how do you measure that compared to others? Displacement of land surfaces, way out there, you might not even realize it for a long time. And tsunamis, well, that would be only if the earthquake occurred in the ocean to create a tsunami, okay? So not probably the best way of measuring that. But that's how they first started doing it, and I believe he was an Italian guy, it sounds like it anyway, Mercalli scale is a relative intensity. One earthquake compared to another, relative intensity. 1 would not be felt at all, and 12 would be total destruction with visible ground waves. So this would be the most massive. So 1 to 12, and it's pretty relative. Oh, that looks like about a 7.5 or a 9.2 or something like that. Not a very specific scale relative to other earthquakes. Okay? Now, before we move on to the other scales, they stuck this in here. And frankly, I don't think many of us will probably ever be in an area that suffers a major earthquake. I sure hope you're not, okay? But, I mean, it could happen. Friends of mine that are in our Sunday school class, their daughter lives in California now, so she could be, in an earthquake-prone area, okay? So that could happen. You could be visiting out there. They do have earthquakes out east, but they're not usually very major. But if you ever are in a place, or you have a friend or family member who is, here are the earthquake safety rules from the National Oceanic and Atmospheric Administration. The acronym for that is NOAA. Not quite like Noah of the Ark fame, but NOAA, not NOAH. NOAA. During the shaking, now this first one's really easy, right? Don't panic. You know, if the building starts shaking, oh, don't worry about it. But don't panic. Don't do something stupid just as a knee-jerk reaction. Don't panic. If you're indoors, might as well stay there, okay? Building starts shaking, you know, probably stairwells and certainly elevators, not the place to be. So seek protection under a table, a desk, in a doorway. Those doorways are fairly strong structurally. Stay away from glass, move away from the windows, you know. And then here, I don't know if you would not think of this, to say the power goes up, okay? Well, then somebody light a match and light a candle, right? Well, if you think back here, fires, if we have gas lines in a building, and you may not know whether there are or not, I'll guarantee you there are gas lines in this building. They use them in chemistry labs and places like that. So there are gas lines. If you light a match because the power went off, if you haven't smelled it yet, you might realize, not for very long, that there's gas leaking out because you could start an explosion. So don't use matches, candles, or open flame. If there's a fire, put it out quickly. Okay. Now, if you're outside, move away from the building. Okay, that's the time to get away because if the building comes down, you don't want to be under. Move away from power lines. You don't want to be under them if they come down. Stay out in the open. Don't run through or near buildings. Okay. Now, this wasn't an earthquake, but I have a special relation to that. My summer between my freshman and sophomore years of college, I was in Navy ROTC, and I spent 6 weeks at sea learning some of the things of what goes on board a ship. The first 3 weeks we traveled across the Atlantic and went to Rota, Spain, and swapped ships, and then the next 3 weeks on the ships they were replacing, got on those and came back. It wasn't very exciting, but it was new and it was an experience. But I was so much looking forward to getting home, and that happened to be the year, or one of the years, that Bob Denver's song was out, Country Road, Lead Me Home to the place where I, blah, blah, blah.
Country Road, Take Me Home.
Huh?
Country Road, Take Me Home.
Take Me Home. And I lived out in the country in Georgia, and I was really anxious to get on that country road and go home. And my folks were planning to come up and meet the ship when it came in, because we were homeported at Little Creek, Virginia, which is near Norfolk, and my mother had several brothers and sisters who lived in the Norfolk area, so they were planning to go up, visit them, and be there when I got in. I was so looking forward to doing that. We got in, and everybody made their way off the ship, and people were coming on the ship, and lots of hugs and kisses and all like this. Well, I was a midshipman. I'd only been gone they had been gone 6 months. So I let all that die down, and I kept looking on the pier, and looking, never saw a family member. What is going on here? We finally got telephone service hooked up, so I called my aunt, because I knew her number. She lived in the area. I said, any idea where my parents are? And she said, oh, you probably didn't get their letter, because we were out at sea. Your little brother was burned in the fire. I went, what? Yeah, well, later I found out it wasn't as bad as what it sounded. He had gone into town. We lived out in the country. Spent the night with a friend of his in town. And Waynesboro was not a very active town, so they were just tooling around, driving around, being dumb teenagers. When they heard the fire trucks going off. we have volunteer fire departments. They thought, oh, let's see if we could go help out, which really was not a bad thing to do. And it was in an area of town where the houses were real close together. They were very old houses, totally wood structures, and once one of them started burning, they just cascaded. So that's where the fire was, and there were people down the street from the house that was burning that were trying to get their belongings out of their houses in case it came to them. So my brother and his friends started helping them move the furniture outside, away from where they thought, the fire came, their stuff would be safe. Not a bad thing to do. I commend him. I never would have suspected he would do something so altruistic as that. But he and Jim were doing that. Well, the fire died down. It burned one or two houses, but they got it under control. And so Dan was walking between the last house that burned and the next house, trying to move the people's furniture back in, helping them do that. Well, some volunteer fire person had the hose there, and the fire was over, and all that was left standing of this one house was the chimney. He thought, oh, wouldn't it be cool to spray the chimney and watch it, because it got really, really hot, and watch the bricks steam, So he did that. Right as my brother was walking between the houses near the chimney, and the chimney collapsed on my brother, and everywhere that the hot side of a brick was against skin, he had third-degree burns. Probably hit him in the head, but he was really hard-headed, so it didn't do any damage there. But anyway, he had been, and by the way, my parents were out of town. My older brother was going on his midshipman cruise. He was between his junior and senior years, and they had taken him up to New Jersey or somewhere to fly out. And actually, he and my younger brother got into a spat that morning. They were going to take him, and Dan decided he didn't want to go. He wanted to go into town and spend with his friend, not with my brother. Anyway, you know how brothers are. So my parents were driving back from New Jersey, or wherever they had gone to take my brother, and Dan was in Waynesboro, the fire, and they took him to the hospital. They wouldn't do a thing for him until they got parental consent. Of course, this was back before cell phones and things like that. They had no way of getting in touch with my parents, so it was a mess. So anyway, they were recovering. My mother is a registered nurse, so she was taking care of my brother, younger brother, and so they couldn't leave the farm to come up and see me. So, but if you're outside, move away from buildings, stay in the open, don't go near buildings. Now, this is a fire, but the same type principle. That chimney, that wall, nothing can fall down if there's an aftershock or something, so don't go near buildings. If you're outside, stay outside, get in the open. If you're in a moving car, stop, okay? As quickly as possible, stay in it, okay? The shocks of the shaking of the earth, the chassis of the car will take care of some of that for you. But do not stop under a bridge, okay? Or a railroad overpass or something. That may collapse on you. But stop out in the open somewhere. The car springs and stuff will absorb some of the shaking, and it will offer you some protection as long as you're not under something that's going to fall on you. You don't want to be there. Now, after the shaking, check, but don't turn on utilities yet. See if they're on. If they're not, don't mess with them, okay? If you smell gas, and most gas has an odorant put in it. Natural gas is not, you can't smell it. So they put an odorizer in it, so you'll have to smell it. So if you smell gas, open windows, shut off the main valve if you know where that is. Leave the building, okay? Don't care if it's raining or what. Get out of the building. Report the leak to the utility. Don't re-enter the building until all has been checked. Now, if the water mains are damaged, shut off the main valve if you know where that is. If the wiring is shorting out, find the switch in the meter box and turn off power to the building, if you know where that is. If you don't, just get out of the building. Okay? If you still got power, turn on your radio or television, if possible, for emergency bulletins. Now, a lot of places, this is more for weather, but a lot of places will have radios that will operate without. Okay, they could be battery operated, or they have some that you can turn a crank and charge the battery and get a little bit of time on it. Television only if you have electrical power. Stay off the telephone. Okay, and that really includes cell phones. This was written back in the day when you didn't have wire-to-wire telephones, because you need those circuits open for emergency. You don't want to be clogging the lines. Y'all don't remember this, but I can remember on Mother's Day you can hardly get through to call your mom because everybody else was calling their mom. All the circuits were at about the same time, and you couldn't get through. Okay? Well, if there was an emergency like this, some of the lines go down, there's fewer lines out there, and if you're taking up space, they can't get through. So stay off the telephone except to report an emergency. Okay? Stay out of severely damaged buildings. There could be aftershocks. There's never any warning. They just happen. Okay? And if they do happen, things that were loosened before now could fall. Stay out of buildings. Don't go, oh, you should see this building. It's really a bad thing. No. And don't go sightseeing. Okay? Because, I heard Inslee really got hit. Well, don't run to Inslee to see how bad it looks. Don't. Stay away from there because that will hamper the efforts of emergency vehicles. We've had that with tornadoes. Okay? People have gone to see the area. They heard this area of Oak Grove was really hit hard. So everybody goes running up to Oak Grove and they can't get through, and people are dying in the back of an ambulance because the roads are clogged. Okay, so don't do it. Stay away from the areas. Let the people, emergency people and repair crews get there and do what they need to do. All right. And again, that's Noah put out that information. So let's go back to the scales. Okay, that's from a college scale. Not the best of scales. Okay, it just goes on how much damage seems to be done. Okay. Well, an American guy, California no less, Caltech, Charles Richter, he came up with a scale way more scientific than, how bad was the damage? This is called the Richter scale. And this is based on the swings that you see from the seismograph recordings. Okay? So this is the Richter scale. It's based on how much movement you have of the earth. Okay? It's a log scale. Now, does anyone know what we mean by a logarithmic scale? What a log scale does, it basically goes by exponents. So 10 on a log scale would be a 1. 100 on a log scale would be a 2. 1,000 would be a 3. So it takes a huge range of numbers and gets it down into a very small range. Okay? Now this scale, because it's a log scale, 3 would be, remember on Macaulay that was a 1, was not felt. 3, you wouldn't be able to sense it. The seismograph senses it, but you wouldn't sense it. Okay? The largest recorded so far has been a 9. And this was an earthquake that occurred in Alaska. I mean, a major one, but it was many years ago. Alaska wasn't all that well developed by that time. There weren't any fuel, oil, and gas lines running all over the state like they have now. But there was a major earthquake happened there. The tsunami from Alaska wiped out portions of Hawaii. It was that big of a wave of water coming off this earthquake there. Huge, massive earthquake. I think recently we've had one more that was either 9 or awfully close to 9. These are major earthquakes. So here's the measures on the Richter scale. 0 to 2 are the smallest detectable earthquakes. Only your seismographs are going to see those, and only the close ones. Okay, 2 to 3 detected and measured but not generally felt. Okay, so 3 is still not felt. 3 to 4, they're felt as small earthquakes, no damage occurs. Okay? I can't remember how many years ago it was, not many. I'm guessing 4 to 5 years ago. There was an earthquake somewhere up in Virginia. I said the East Coast sometimes does have earthquakes. There was an earthquake up in Virginia. Now, close to that quake, and it must have been maybe a 4 or 5, because there was some local damage. But it was felt at the farm, our family's farm in Georgia. Okay? There it would have been, if it occurred there, a 3 or 4. They felt it. People said they felt something move. We have a small 2-bedroom bungalow on our part of the farm. When my parents died, they left the farm to the 4 of us kids. So my older brother lived there, my younger brother lived there, my sister lived there. We were the only ones who didn't. So we built a little house so that when we go there, we don't have to bum in with them. Because quite often they have family there anyway. If it's a major occasion, they don't have room. So we just decided to go and have a place there and improve the value of the farm too. So anyway, we did that. And earlier, my wife's sister had given her a thing that just said farm that we hung on the wall because we lived on the farm, had the house on the farm. Well, when we got there, it was on the floor. I thought, why is this on the floor? And I mentioned something to my sister-in-law, and she said, oh, that must have been when the earthquake. We just got a little bit of shaking, nothing, no damage. So that would have been 3 to 4. You could feel it, but no damage. But where it actually occurred, that was probably a 4 to 5. Now, how do I know that there was some damage? I said it was in Virginia, probably somewhere in eastern Virginia. Washington, D.C. is real close to eastern Virginia. You know the Washington Monument in D.C., that tall obelisk? It made a crack in it, okay? So there was some damage. There used to be stairs that you went up, you could walk to the top, because the Washington Monument is the tallest object in the District of Columbia. No building can be higher than the Washington Monument. I believe that's the case. And you could go up to the top and you could see all around, all of the District of Columbia, bird's eye view. Well, they shut that down because there was some damage, some cracking to that monument. And I think it's reopened now, but it was down for quite a while. So that's 4 to 5. Minor earthquake with local damage. 5 to 6, a moderate earthquake with structural damage. Okay? 6 to 7, strong earthquake with destruction. Okay? Whole buildings will be destroyed. 7 to 8, major earthquake, extensive damage and destruction. And the 8 to 9, an enormously large earthquake, total destruction of just about everything. Okay. Now, again, this was probably 7 to 8 years ago. Sometime there was right at Christmas time. There was an earthquake that was really close to Haiti, which is the poorest country in the Western Hemisphere. And boy, did it cause tons of damage, really near the capital city, and buildings, houses, homes, just wiped out. I mean, major, major damage. It was probably in the 5 to 6 range. Now, on the Mercalli scale, that would have been 10 or 12, But no, it was really just this. The trouble is Haiti had no, I don't want to say no building codes. They probably had the codes, but no one followed them. Their houses were concrete block. It was just a very poor country and very poorly done construction. And buildings just collapsed and stuff. Within, I think it was just 3 to 5 months of them, in Chile, that's on and again, you don't expect earthquakes near Haiti. That was in the Gulf of Mexico. That's not where you have plate tectonics and stuff going on much. Some, but very little. But in Chile, South America, that's in the Ring of Fire, okay? Lots of seismic activity going on there. Lots of plate movement. They had a really major earthquake. I'm pretty sure theirs was 67. May have even been 7 to 8, but it was major. You see, Chile had so much of this. They had very strong building codes, and they had nothing to withstand these kind of earthquakes, but they had minimal damage for the size of earthquake. Much less than Haiti did, but theirs was a much stronger quake. So based on Mercalli scale, that would have been a less powerful quake. And it wasn't. The real strength here was measured by seismograph. That was a much stronger quake, but they had much better building codes. Now I want to go back. I don't think. Okay. No. Let me go back to this. It's a log scale. Okay. I want to mention this because this is important. It's mentioned in the book, but in case you missed it. What this means, like I said, a 1 on a log scale might be a 10, 2 would be 100. So everything on a log scale is a power of 10. So there are some questions here in the text. Let me see. Okay. The first group of questions, 19.3 and 19.4, are talking about the time difference that we did here of earthquakes and the distances. So those are really pretty good questions to look at and think through. Some of them are, almost a little silly in the fact that you can answer the question without doing the way they say to do it. But we'll leave that alone. But here, 19.5, and I wanted to point this out to you. Here it is. On page 492, an increase of 1 on the Richter scale means that the amount of movement of the ground increased by a factor of 10. Here's Corey. Right? I have to go all the way across the page, and the lines don't line up too well. So, by a factor of 10, the amount of movement of the ground increases by a factor of 10. The amount of energy released is a factor of 30. Okay, because energy depends on the square of some objects, so it goes up by 30 times. The amount of movement, 10 times for every point you do. An earthquake measuring 3 on the scale is usually not felt, blah, blah, blah. Okay, we already said that. Okay. Now, even though it says here, and all right, here's coal, right? We'll talk about earthquakes and earthquakes measurements. Okay. Even though they say 9 is the largest measured so far, and they only go up on the next thing to 8 to 9, that doesn't mean there's a max. Okay? On the Mercalli scale, 12 is max. Okay? That's total destruction. This is based on actually movement. Okay? It can go higher. We don't expect and we hope it doesn't, but it could go higher. There is no upper limit. Okay? Now, here's the other thing. Here's example 19.5. Compare the energy released by an earthquake of 7.2 magnitude to an earthquake that with a magnitude of 5.2. Now notice they said the energy. That's a factor of 300 for every point it goes up. Well, guess what? From 5.2 to 7.2, here's 5.2, moderate earthquake with structural damage. 7.2 would be a major earthquake with extensive damage. What's the energy difference here? Every point it goes up 30 times. 30 times 30, 900 times the amount of energy released from a 7.2 from a 5.2. 900 times the energy release. Okay? Now, compare the amount of movement of the ground, the surface wave amplitude they call it, associated with 2 earthquakes. Well, that's only a factor of 10. So 5.2 to 6.2 would be 10 times the movement of the ground, and 6.2 to 7.2 would be another 10 times, and 10 times 10, 100 times the movement of the ground, the shaking and stuff like that, 900 times the energy release. So the log scale, that goes up big time. Okay. Now, the next slide, and I'm sorry I had forgotten this, is the very same slide we saw here that I had to squint to read, and you probably couldn't read it from where you were sitting, okay? Don't sweat this one. Here it is in much bigger print. This is what that was saying. I've already gone over it, so I will sort of not do too much on this. I think we hit just about everything there. Again, let me emphasize, if you're in a car, bring it to a stop, but bring it to a stop out in the open. Just like it says here for you, if you're outside a building, stay in the open, get your car into the open. Don't park it under a big tree. That tree may fall on you. Next to a big house. That house may fall or a building may fall. Don't park it under a bridge. The bridge may collapse on you. Do it out in the open, but stay in the car, okay? Come to a stop as soon as possible in a safe place, but stay in the car, okay? If you're underneath a bridge, get out from under the bridge, come to the shoulder of the road somewhere where there's nothing that can land on you, and stay in the car. If you're in your car and your car is running, you can listen to the radio in there. Not a bad place to be, so you can find out if you need to get off the road or something like that, if there's an emergency needing to get by. And they say a little bit less, but stay out of damaged buildings. It could fall on you. And do not go sightseeing. It's just not worth it. You need to stay out of the way for rescue people, emergency responders, and repair crews, and, electrical repair, whatever. Get out of there. Don't clog up the issue. Okay. All right. And for those who did come in, let me just recap this. We're continuing in chapter 19. I think we'll finish before 3:15, and we'll go on into chapter 20. It follows directly, really similar. Then at 3:15, we start the lab for chapter 18. And it's not directly for 18, but that's one that goes with it. And it's going to be a very short lab to do, because there's only 10 points worth that we'll actually be doing. The other 15 points will be from the questions at the end of chapter 18. There's questions for thought. These are not the multiple choice questions. These are just the short questions with fairly short answers. You'll have to read through the chapters to find the answers. Questions for thought and for further analysis. There's 16 questions for thought, 4 for further analysis, and you just write those answers down on a piece of paper. If you need to distinguish between those, QFT for questions for thought, FA for further analysis. Just 1, 2, or 3, or 4 of those, but you do 15 or more of those questions, and that's going to be the last part of your lab. Now, highly recommend you work on those questions before your test. That's a great way to study. That's why I told you about this last time, that this was coming up. So you could have had the weekend to be working on that lab if you wanted to. But if you haven't, you can work on it today before you take your test. But by 5:15, we'll have to terminate all that question writing and stuff like that, or anything else, and get started on your test. Because the test for Chapter 18 is today. And since we're probably going to finish 19 today, and probably even get started in 20, then Thursday we'll again have 2 hours of class, probably in Chapter 20. I don't think we'll finish that, but if we do, we'll move on to 23, I think is the next one. And then just continue going like that. And here's Patel, and I think he heard it all before, so I won't go over everything again. I couldn't remember if the others have been here or not. Okay, so how are we doing time? Not quite 2:30. Okay, everybody got this? Yak, until you got it done. Earthquake safety. All right, now we go to 19.4. If you recall, the title of the chapter is Building the Earth's Surface. And what have we talked about so far? Just a quick review. Interpreting the Earth's surface, Earth's changing features, and earthquakes. That didn't sound like a lot of building of the Earth's surface to me, did it to you? Now we see where that was going from. We're going to be talking about the origin of mountains. This is where the Earth's surface has been built, how it's been built. Okay? So I guess maybe a first thing is a good definition here. What is a mountain? An elevated part of the Earth's crust rising abruptly above the surrounding surface. Now, one of the pretty good movie, pretty funny movie, but it was a pretty nice movie, was The Man Who Went Up a Hill and Came Down a Mountain. That was the name of the movie. Any of you ever heard of it? Maybe not. Probably before your time anyway. The English actor who did a lot of the romantic comedies, Pride and Prejudice, or no, not Pride and Prejudice. Some of those Jane Austen type things. He also did with Julia Roberts, Notting Hill. Y'all know who I'm talking about? Can't think of his name now. But anyway, he was in this movie. And what it was a story, I think in Wales, in England, of this survey crew that was going out, making their geologic surveys. They did it every 10 or 100 years or something like that, and they were out there doing it. And they determined this mountain that this city was or little village was very proud of because it had their name. It was thus and so's mountain. They went up and measured it and found out it wasn't quite tall enough to be classified a mountain. Okay? I don't know what the discrimination was, but they were a few feet or yards or meters short of being classified a mountain. So it was going to be downgraded on the next survey as a hill rather than a mountain. Okay? And it was sort of a funny movie and had all these other things going on. But basically, the storyline was that the people in the town started hauling rocks and soil and everything else they could get from low down and hauling it up their mountain to make the peak a little bit taller so they could so it's The Man Who Went Up a Hill but Came Down a Mountain was the title. So that's what it needed to be. Elevated abruptly over the surrounding surface. Now, these are created three ways. The first two ways is the folding of the crust, and we talked about that earlier. That is one of the strains that comes, especially if you had plastic-type material. Folding of the crust. Now, most of the time that folding happens much deeper than the crust, where the rock is hotter and it gets folded. More commonly, or I want to say more commonly, but I think more commonly, is faulting of the crust, where actually the either tensional forces or tensional forces or compressional forces are either causing normal faults or reverse faults to happen, and that kind of motion happens, and that is what forms the mountain. So either folding of the crust or faulting of the crust. That's actually a break in the crust. So here it says 2, here it says 3. You have folding, you have faulting, and you have volcanic activity. And that's the one we usually think of for most of our mountains, perhaps, but it's probably not that prevalent, but they're definitely beautiful, noteworthy mountains from the volcanic activity. Okay. Everybody got it? Okay. So let's first look at folded and faulted mountains. Now let's begin with one, domed mountains. This would be folded. Okay? Begin with a broad arching fold. Now what do we call an arching fold? There is a name for it. Back early in the chapter. Arching anticline. The trough would be called the syncline. Okay. So this would be an anticline, broad arching fold. These would be your dome mountains. And I'm not absolutely certain it's one, but I think Stone Mountain in Georgia is probably a dome mountain. Okay? Now, what has happened with those is overlying sedimentary rocks weather away, leaving the more resistant granite peaks. Okay? Now, much of the Appalachian mountains are folded mountains. They're ancient mountains, some of the oldest on the planet, the Appalachians. Okay? And actually, the folding occurred long times ago. It hasn't been folding lately at all, so actually the Appalachians are getting shorter because you have the weathering, the erosion, and other things. They're losing elevation, like that mountain in that movie. It had actually eroded down, so they started building it back up. Okay? Those are folded mountains. Here is sort of a picture of what's happening there. This is the doming action that happened. Broad arching folds are happening here in 2 dimensions, and this doesn't happen immediately. This happens really slowly. I mean, imperceptibly slowly. You'd have to be hundreds of thousands of years before you notice, hey, that's getting taller, isn't it? This is happening probably because there's some pressure underneath here pushing up on the crust. And when it pushes up on the crust, you have this doming going on. Well, after a while, if you think about this surface here is being stretched because it was flat and now it's like this. Well, it's being stretched, and where it's being stretched, you have crevices, cracks, and then you have rain, wind, and they start eroding away. So what you wind up with is a much smaller than what your original dome was, but this is where the underlying granite, the underlying sedimentary rocks weather away, leaving the more resistant granite exposed, and that's probably what a lot of the Appalachians are places where that's happening. Even though you don't see the folding necessarily, you see that it was folded because a lot of it is eroded away. Now, the picture in your text on page 493 is an aerial view of the Appalachians, and you can almost imagine the folding that's going on when you look at that. Everything is lining up. And when you look at a map of Jefferson County, you see, for instance, Red Mountain and Shades Mountain and Double Oak Mountain. They're not a single peak like this, like a volcanic mountain would be. They're a ridge, a long ridge. And you go up here, you go up here, you go up. It's a ridge, and that's the broad arching fold. That's what created these, my guess, okay? They say here under this picture of the Appalachians, the folded structure of Appalachian Mountains revealed by weathering and erosion is obvious in this Skylab photograph of the Virginia, Tennessee, Kentucky border area. The clouds are over the Blue Ridge Mountain, over up in the upper left, and you see why they were called Blue Ridge. They almost look that way. Okay, so those are your, especially your folded mountains. Okay, everybody got this? Still writing? Okay. Then let's go to faulted. And these are often called fault block mountains. They rise sharply along steeply inclined fault plains. Okay? Now, over time, weathering does erode away the sharp edges. But when you look at a mountain range, like the Appalachians, all you see is these smooth, rounded, no peaks. I mean, yeah, there are peaks, but they're nice, round mountains, okay? That's because erosion has worn off the edges. Go to fault block mountains, and if they've been there long enough, they will look rounded too, but the Rockies, if you've ever driven toward the Rockies, you know they don't look very rounded at all. You can see individual peaks, they're jagged looking. That's because they're still rising. Their weathering has done very little erosion on the sharp edges. Now, you'll see some that has, okay, especially if there's softer rock, okay, but the hard granitic rock, it'll maintain those sharp edges for quite a while, okay? Now, this picture sort of illustrates this. Remember, earlier we talked about horst engravings. These are some of those. I don't think those are very important words, but that's what we were talking about. When they first happen, everything is sharp and angular. But over time, erosion wears down the edges and the corners and fills in the gaps. So basically, your mountain doesn't rise as abruptly because it's worn down and the surrounding areas are filled in. So erosion does both of those. It rounds out the mountaintop, but fills in the valleys. So now you have a less distinct thing. So this, at one time, could have been a mountain, and then later was just a hill because it wasn't tall enough to be a mountain. And there, Melanie snuck in when I wasn't looking. But it's good to have you. All right. Anyone else do the same? Okay. So the weathering erodes away the sharp edges and also fills in sediments in the lower areas. So what was a distinct rise above the surface now is a lot less distinct because the upper parts are worn down and the lower parts are filled in. So you have less of a contrast, you might say. All right, so those are folded, then faulted mountains. Now let's move to volcanic mountains. Now what is a volcano? Well, usually it's an elevated part because magma has come out as lava and has built up the area. So it will be at least a hill, sometimes a mountain, formed by the extrusions of lava or rock fragments from the magma below. Magma if it's below the surface, lava if it's on the surface or above. Now, remember that magma may contain rock fragments as well as molten rock. So some of those rocks come out solid, some come out liquid that then later solidify. So you have both of those going on. Now, they have this little statement here and never describe it, okay, per se. But I will leave it up here. The structure of a volcanic mountain, you have a vent, you have a crater, and you have the lava flow. Now, they never fully defined vent that I found, but I'll try to point it out to you. Okay? Now, this, I'm pretty sure, is Mount St. Helens after the eruption back in, what was it, 80. Mount St. Helens, several years after the explosive eruption. Okay? Now, do you think that volcanic mountains grow when they erupt? I always assume, yeah, they grow because more lava comes up and builds more side, so it's growing. Not Mount St. Helens. Mount St. Helens was plugged, and the pressure underneath, when it finally gave way, it blew the top of the mountain off. So actually, Mount St. Helens got shorter after the eruption than it was before because it literally blew its top. Okay? And downhill from there, big chunks of what was the top of the mountain went rolling down, probably causing a lot of damage. So the vent was somewhere in there. Okay? This is steam that's coming out. This isn't lava or anything else. This is steam because there's still vents there, okay, that are coming out. So the vent is somewhere in there. The crater, you can see the outline of at least part of the crater there. That's the crater, usually nearly circular or somewhat circular pattern there. And then the lava flows, you can see where the lava flows were there, going down the sides of the mountain. So that's the obvious one. Crater is pretty obvious. The vents, that was the crack, the edifice, the orifice, I guess you could say, that opened up that the original stuff came out of. Okay? That's all they say. They just say these words and never define them. Okay? That's my best guess at a definition. All right. Here are how we classify volcanoes by, I guess about the only classification we got. First of these is called a shield volcano, and it's constructed of solidified lava flows. Okay? It's characterized by broad, gently sloping cones. Sure, there's a rise in the middle, but it's broad, gently sloping. Much of the Hawaiian islands are formed by these shield volcanoes. I mentioned I was in the Navy. The type of ship when I was stationed on my first tour of duty as a full-time, was an ammunition ship. And I learned then that ammunition ships are named in a pretty bizarre way. Most of the ammunition ships are named after volcanoes. Okay? Fairly appropriate, because if you ever have a fire on an ammunition ship, you probably are going to have a big hole in the water, and that's about all that's left, because you're carrying really highly explosive stuff. So there's really no safer ship in the Navy than an ammunition ship, because everybody knows fire safety and really obeys it and is very, very strict. Okay? We had many general quarters where we practiced responding to a fire. We only had one fire in the 3 years I was on there. A mechanical room where the ventilation for, or may have been the air conditioning for the radars for the gun, the fire control for the gun, firing a gun, not other fire control. A bearing went bad and something started heating up, and there was a little bit of smoke, no flame at all, way away from anywhere there would have been any ammunition. But boy, that thing was dealt with, and that was really, really quickly. Okay, that was the only general quarters we had because of fire, and it was minor, very minor. They got that bearing repaired and everything was back to normal. So shield volcano, and how it got me started on that. The most active volcano in the world is the ship I was on, the Kilauea in Hawaii. It's been erupting constantly for years and years and years and years and years. It just spews out lava. It's not a major eruption thing. Now, a couple of summers ago, it really started spewing out a lot more, and the magma from the lava from it was covering roadways, eating up fields, knocking down houses, and no one could do anything about it except hope it's going to get over soon. It did die down, but it took a month or so for that to happen. And now it's still going out, but it's just not as major, okay? But that's shield volcanoes, broad, gently sloping cones formed from the lava flows, okay? The second of these is the cinder cone volcano. Let's see, I think they have pictures of the shield here. Yeah, this is the one in your text, figure 1921, okay? This is Mauna Loa. Well, here's what forms these shield volcanoes. Gently sloping. You have layer after layer after layer of new magma on top of boulder on top of boulder as it goes off. These, I think, are what they call the vents, where the lava comes to the surface. That's the vent. This is the lava flow. And what was the other? Oh, the crater. This one is actually broken the surface in several places. Those would be your small craters. Mauna Loa, there was also an ammunition ship called Mauna Loa, Mauna Kea, Vesuvius, Shasta, Mount Hood. The list goes on and on and on. Okay. Now, in the old days, they also had other names like Pyro and Nitro. They named ammunition ships after them. Now it's mostly volcanoes. So this is your shield volcano. Okay. Not really all that impressive, but still, pretty impressive. Now, the cinder cone volcano, we don't have a picture in the slide set. I wish they did. I think there is one in the book, and that's figure 1922, Sunset Crater, a cinder cone volcano near Flagstaff, Arizona. Okay? Nice picture, by the way. Cinder cone volcano is constructed of rock fragments, which is called the cinders. Okay? Not lava so much as rock fragments that have been thrown up. It's steeper and smaller than the shield volcanoes. So it will go much steeper, but a much smaller area than the shield volcanoes. Nice looking, but pretty small. Okay? And then the third kind is your composite volcanoes. And these are alternating layers of cinders, like you have in the cinder cone, ash and lava flows, mixed with volcanic mud, just all sorts of things building up as it goes. And this would be the composite volcano. Lots of vents here, or potential vents. At one time they may have been vents, not anymore. Maybe one up there. Lava flows, the crater here, obviously there. Now this is Mount Shasta, I think. I believe it's a different view from the one you got in your book. Still a very impressive volcano, a composite volcano. I think this is part of the crater here. Obviously, its last explosion blew the side off the mountain. Left the peak over here, but blew this part over here. And you can see, underneath the snow and stuff, you can see the lava flows coming down like that. There's the crater. No active vents right now. It's not been active as long as we've been, anyone's seen it. But sometime in its past, it obviously had activity. Okay? But the alternating layers, cinders, which are rock fragments, ash, which would, when the burning stuff happened, the trees or anything that were on it, turned to ash. Lava flows, that would be the molten rock that's solidified. Now, the volcanic mud, they don't do a good job of describing that either. But lots, as you saw before, lots of vapors, water vapor, steam, and stuff like this come out of these two, and that watery type material contains in it some of the ash and some of the other material, and that's what makes the volcanic mud, the mixture of that with water. And if it's been doing that for a long time, that may really have the whole area fairly damp, and that would be the volcanic mud. All right. This part is called Other Features. Now, before we get to it, there is a really nice blurb on page 497, Volcanoes Change the World. And it mentions a few of the bigger, more massive explosions. Tambora in Indonesia, 1815 to 1816, and how wide the effects were. That volcano in Indonesia, basically on the opposite side of the globe from us, okay? Way over in Southeast Asia, okay? It threw so much ash and other material into the atmosphere, more light was reflected from the sun and energy reflected from the sun, very little, a lot less got to the surface. And get this, it snowed in New England in June of 1916. Snowed in June of 1916, and the cold continued into July. Crops failed, and 1816 became known as the year without summer. One volcanic eruption, a massive volcanic eruption halfway around the globe, influenced the weather in New England. Okay, they can change the world. Okay, in 1982, the eruption of El Chicon in Mexico created enough haze in the stratosphere to reflect 5% of the solar radiation away from the Earth. Researchers also estimated El Chicon eruption cooled the global temperatures by a few tenths of a degree for 2 or 3 years. So sure, global warming and global cooling can have other things influencing it, including the eruption of volcanoes. That dropped the temperature for several years of the Earth by a few tenths of a degree, which is what we're worried about now, going up by a few tenths, okay? One volcanic eruption, okay? And if you read on, in June 1991, the Filipino volcano Mount Pinatubo erupted, blasting twice as much gas and dust into the stratosphere as El Chicon had a decade earlier. Dust from Mount Pinatubo remained in the Earth's atmosphere for the next 10 years. The haze from such eruptions has also potential to cool the climate, and so on. This is probably 5 or 6 years ago now, a gal that sat right back in there somewhere, she moved around some, was actually from the Philippines. She remembered a little bit of the Mount Pinatubo eruption, but remembered hearing stories of it big time. And that's what she did her research paper on, the Mount Pinatubo eruption and what it did to that major eruption. And it had effect on the climate, of the whole world, not just in the Philippines. Major influence in the Philippines. Now, I was trying to think, more recently from this, they've had another one in the Philippines. It may not have been that major, but it was, whole villages were wiped out, and people were not able to get in touch with friends. We have several Filipino friends, and it was pretty frightening. All right. Now, this was in the last, I'd say, 5 years or so. Remember we mentioned Iceland as a volcanic island? Iceland had some, not that major of eruptions, but did have some eruptions of their major volcano. And it was enough stuff blown into the atmosphere and the wind carried it over to England. They had to shut down airports all over England for days and sometimes weeks because there was enough dust particles in the air that if the airplanes had sucked it in, they'd have blown out their engines. That wasn't major climate change or anything, but it sure was a major economic and political and all sorts of changes happened just because of a volcanic eruption. All right. Now we're ready for the other features. This is the bottom of page 497, and here's a really true sentence you may not think of. Most magma, that's molten rock, remains underground. It doesn't make it to the surface. It doesn't get blown out of a crater of a volcano. Okay? It stays underground. It cools and solidifies to form intrusive igneous rocks, intrusive inside the Earth's surface. And here are a few of the rock formations that do come out of that. Okay? I want you to pay attention to these. Okay? Here's the figure that shows it. The first of these is a batholith. That's a big, broad area, a large amount of crystallized magma over a broad area. Now, it never made it to the surface, but the surface over it eroded away after it was crystallized. So you have this kind of formation showing up. It is from magma, but that was all covered with soil and other layers, and it just made its way up. So that's the broad, large amount of crystallized magma, the batholith. A little bit smaller than that is your stock. It made its way up. Now, they're showing here sedimentary rocks on top, and that's pretty common. This is an area covered with sedimentary rocks, and it may have soil itself on the very surface of that. But the stock forces what batholith, big extrusion of magma. A stock is a smaller protrusion from a batholith. Okay, so it was here. It made it up through several layers, but not as major as the batholith was. Okay, came out of that. Now, the batholith intrusions that came up could form what we call a hogback. And what this is when the batholith folded the sedimentary rock, and what was horizontal now is vertical, you get ridges in here, and they call that the hogback. Okay? Kind of like Arkansas's razorback, you know, those are wild hogs. But that's the hogback. The batholith intrusion can cause hogbacks. That would be a rough area here made up of folded sedimentary rock. They're not, the hogback is not magma, crystallized magma. It's sedimentary rock, but it's roughened and has been forced to the surface. Okay. Other related processes are what they call dikes. Now, the dikes are almost vertical protrusions, not a big broad thing like a batholith or a stock, but just places kind of like a vent, small vents on a volcano, just a place where the magma at some point made its way through weaknesses or cracks in those sedimentary rocks and made their way up. They're somewhat vertical, don't have to be totally vertical, but going mostly up through cracks in the sedimentary rock. The sills, on the other hand, there they are. Okay, these are the horizontal layers where the dike, the vertical, found a weakness between layers and filled that. Then that would be called the sills. None of this ever made it to the surface. But here you have sedimentary rock with protrusions of the dikes, vertical protrusions of igneous rock, and then layers of igneous rock in between the layers of sedimentary rock. Okay? And those are the sills. The horizontal layers would be the sills. And then finally, the last one they list here is the laccolith. Lith means batholith, laccolith, that means rock, basically. The laccolith would have been a sill if it was deeper, but it was a major dike that came up and went nearly to the surface, and it got close enough to the surface. It folded the sedimentary layers on top of it and made a little hill. This is probably a laccolith here too, and that. Folded up, and that was much more major because the sills happen deeper with more overburden on it, so you don't have as much. But it formed a little mound here. And that may have been what Stone Mountain was. I don't know. This is more peaked than Stone Mountain was, so something else is going on there. But this was igneous rock. Intrusive igneous rock. And these are what do they list here? 1, 2, 3, 4, 5, 6 different types of structures, features that show up with igneous rock, the magma that didn't quite make it to the surface. Okay? These are the other features. And I think that closes out. Oh, wait, here's the overall picture. Okay? I don't know if this is in your text quite in this way, but here it is. Mountain ranges are composites of many different processes, each uniquely structured. No two are exactly the same. The general classifications are folded mountains, where the things such as, on a bigger scale, say, like the batholith here, okay, or the hogbacks, actually, folded areas here that form a ridge, okay? It may have happened way, way deep, long time ago, but erosion has uncovered it, okay? So that's folded mountains. Faulted mountains are when you have the breaks happening and you have the very jagged areas that are left over that may in time erode and you can't tell what's there either. And then volcanic activity. So, and there's all sorts of combinations of these. Now, I don't know of any volcanic mountains in the state of Alabama. There may be some, but I sure don't know of any. I bet you most of them are folded. There could be some that are faulted, and they can be right next door to each other. It just depends on what type of activity is caused. But in the mountain ranges out west, most of those are probably faulted, and every now and then you may have a volcanic peak in between some of those. Okay. All kinds of different processes. This is especially apparent along converging plate boundaries, where they're crashing into each other. The Himalayas, converging plate boundary. Those are largely probably faulted mountains there. But there could be volcanoes where the magma makes its way to the surface. Okay. Now here is, and this is in your text, this figure. The text is in 497, the figure on 498. Okay? This tiny little plate here, probably one of the smallest of the plates, tectonic plates on the globe, the Juan de Fuca plate. Okay? It's being crashed by the Pacific plate here, bumping into the North America plate there. Poor little plates crashed between the two. But look at what happened along that. Probably most of Vancouver Island here is a result of that activity. Just inland from here, probably where Juan de Fuca plate has been forced under the the North American plate, has created a string of mountains. But look how far inland they are. And that's because the subduction has gone under there and goes for quite a ways before you have the activity here. But look at all these volcanic mountains. Mount Garibaldi, Mount Baker, there was an ammunition ship called that. Good Feet, Mount Rainier, that's the one you see right outside Seattle. Mount Adams, Mount St. Helens, that's the one that exploded in the 80s. I can't read all these. Mount, goodness gracious, this is hard. Three Sisters is down here. I can't read that Crater Lake, Mount Shasta. Somewhere in here is Mount. Oh, there's Mount Hood. Okay, I see that now. I think Jefferson is in there somewhere, but I can't pick it out here. But all along here, one to Fuca is responsible for all these mountains. Now, I talk about something a little weirder than these volcanic mountains along here. You know what this brown area is? North, okay, right here. It's plateau basalts. Wait a minute. Basalts are the iron-rich oceanic plate, crust underneath the oceans from volcanic activity under there. And here somewhere on that side of the mountains. Okay? Well, that was one time probably sea itself, and this activity here is built up the Earth's surface and captured these basalts in here. And we actually drove over some of these in Idaho and Montana when we were up there a couple summers ago. We drove through some of these basalts. Okay. Now, the other reason, I think this was one time ocean, Salt Lake. This is the Great Salt Lake right here. And actually, let me see if I can see it on here. This may be it here, the Snake River. I think that may be the Snake River there that forms the boundary, or maybe it's right in here. Somewhere in this area is the Snake River, and I think I told you about it. Its banks are vertical banks that go straight down to the river. I said, Karen, banks are usually sloped. These are vertical. What do we call that? Later we read there was some enormous lake here left over from the glaciers. The glaciers bulldozed their way down, left a moraine ahead of it. That formed a dam, and then behind that, as the glacier melted, they filled the biggest lake probably in the world at that time, covered probably lots of area here. And that bulldozed dam that was left by the glaciers broke, and the water ran down the Snake River for days, maybe weeks, just cutting out more and more because it was running so fast and cut vertical sides, and that's why that was the case. So if the Earth could talk, it would just be amazing what has happened in its history. All right. That's the last slide. This chapter has one of the shortest summaries of all, so here's my pitch. Nothing replaces reading the chapter. I hope you've read it before, and you probably wouldn't be a bad idea to read it again before Thursday. The summary is pretty good, but it's awfully short. It has a lot of italicized words that showed up later as key terms, and that's a fairly short list. Applying the concepts, though, 50 questions, which is on the long side of things. So those are really good questions to study for your test. Okay? Then this chapter's questions for thought, one more than the last chapter, 17, with 4 for further analysis, so it has one more question than the other. You don't have to do these, okay? But there's good things to study for the test. And then the parallel exercises, some of these are probably pretty good, especially those that would deal with the timing of your P and S waves. That you probably could find those pretty interesting. All right, any questions? Okay, we still have, we don't have much time, do we? Pretty close to 3:15 now. Time to start the lab. But let me at least introduce you to chapter 20. All right. Chapter 19 was building the Earth's surface. Chapter 20, on the other hand, is waiting for a PowerPoint to open. Here we go. Is shaping the Earth's surface. Okay? Now, again, I'm not absolutely certain what this is. I'm guessing it could be part of Grand Canyon, but there's a lot of formations that are like this out there. And this surface has certainly been shaped since it was formed, okay? You can tell this was a lot of sedimentary rock. You can tell by the really horizontal layers there. There's some have been folded, it looks like, but then a lot of it's been eroded away. So this is, chapter 20 is going to deal with shaping the Earth's surface. And here's the core concept, which is on your page 505. The surface of the Earth is involved in an ongoing process, and we've seen this just about every chapter. Rock cycles, principle of uniformity, process of diatrophism. I mean, we just see it over and over and over again. Ongoing process of destruction and tearing down of higher elevations. Always is happening. The last chapter was building up. This is tearing down. Okay. Does anyone know where this might be? There's a little bit of a hint. Sort of what color would you call that rock in? Color. Gold or yellow? Yellowstone, you got it. This is Yellowstone, and this is actually, I think, Upper Yellowstone Falls, and there is also a Lower Yellowstone Falls. This is the Yellowstone River running through here, and my goodness, look at the volume and the speed, the intensity of that water. Okay? Here's the part that's almost hard to believe. Wherever up here the sides of this thing are, that's the original soil surface. This river running through here at that kind of rate for so long has dug out this V-shaped valley here. Here's the river running down here, still digging out that valley, and every now and then you have more landslides down and more water is carried away. This dam, the waterfall at the top of it, used to be probably over here. This way. It's eating it away and eating it away and it's still eating it away and eating it away. The waterfall probably used to be out here somewhere or way over here or somewhere, and it's just eating back all the time. This is the most resistant rock here, but it's still being worn away. The Earth's surface is constantly involved, ongoing process of destruction and tearing down. Soil is being washed away, eaten away, eroded away, carried away, and downstream from this is the Lower Yellowstone Falls. They're almost as spectacularly looking as that. There's another place you can take photographs further down. Okay? Really, really incredible. Please, folks, sometime during your lifetime, make it a point to take a vacation out to Yellowstone. Okay? It's expensive, I'll admit that, but you can stay outside the park to go through it. The geological features there are just unbelievable. There's no place on the surface of the earth with that diverse of geological features as you see. And that was our first national park. Teddy Roosevelt designated that the first national park, and it's the oldest, of course, and it's the most impressive. It's just incredible. All right. How are we doing? We're almost there. Well, I guess we ought to stop there. And we'll pick up next time with weathering. Okay? We didn't get very far this time. Some really incredible photographs here in this chapter. Read it. Read it before we talk about it. I think you'll find it helpful and enlightening. So, we'll stop now, take a little break. When we come back from break, if you'll, we'll get ready to do the lab. In fact, I'll go on and pass out the lab to you right now. I may just pass out right now, but let's see. I'll turn off the projector in just a bit. This is one lab we're not going to do in this room or in a computer room. we are going to go down actually to a laboratory and do measurements, okay? And you've heard people talk about a wet lab. This definitely is a wet lab. I mean, y'all are not going to get wet, or hopefully not, but we will be using water with this. So I'm going to go and turn this off for now because we're not going to do it. I'll have to come back and unplug things and move down. But here's your lab. Very short lab. It's going to take me more time to set up than it's going to take time to do almost. But you can be reading this and working on your questions. The best thing you can do to study for the test is going to be the last 30 minutes. That's one over. Another behind it. Another. All right. Let me go down and see. I've got to find out for sure if we can use the lab I want to use. If we can't, I've got to move my equipment to another different lab. So I've got a little bit of stuff to do. So what I'm going to do is shut down this for now. Okay, igneous rock is rock that was formed from the solidification of hot volcanic rock, magma or lava. That's igneous rock. Two types, well, many types, I guess. But one of these types is, lots of ways to classify. Large crystal size, which means they were intrusive igneous rocks, that meaning they formed inside the Earth's surface, cooled slowly so the crystals were large. So those are coarse textured rocks. Now, another way to classify is by whether they're ferromagnesium silicates or non-ferromagnesium silicates, okay? If they're ferromagnesium, they have high iron content, which means they're usually denser than other. Low iron content, they're less dense and also lighter in color, okay, because there's less iron in them. Iron is usually dark. So, granite is a type of intrusive igneous rock. Notice there how large the crystal sizes are. You can see them, definitely, okay? Some of the crystal planes here, you can see the big old broad shiny areas that were where the crystals fractured, okay? Large crystal. And this has quite a bit of iron in it, okay? Quite a bit of black in there, but it's mostly a light-colored rock. This is granite, okay? It says on the side, granite. It's brown granite, so it has more of your plagioclases and other things like that. A lot less quartz than most granite does here in the U.S. Now, the other type is basalt. This is igneous rock formed from the solidification of molten material, but this usually happened in the bottom of the ocean. When the magma came to the surface, became lava, and then cooled rather quickly, so it has very small particle sizes. You can hardly pick out crystals in there. On the edges, you can see just very tiny little crystals there. It cooled rapidly, small crystal size, but notice the color. Very dark, so this is very high iron content. So this is intrusive igneous rock, but low iron content. This is extrusive igneous rock, but high iron content. Okay? Now, we are not going to follow exactly the procedure here, but pretty close to it. Okay? We're not going to tie a string. We're just going to lower carefully. Okay? So let me get set up then for what we're going to be doing here. I hope I brought enough devices. I think I'll use this thing because it will splatter less, hopefully, than that. Wait. This one I don't want me to go there. It pops up here. Okay. This one one of these. Okay. Now, at some point here, I'm going to have to start holding this because if we put so much into this, it will tip and tip easily. So I'm going to have y'all running around and doing stuff after a certain point here. Okay. Now, what we have here is a catch bucket with nothing in it. And this is almost filled with water, though it's not quite. So if someone will run a little more water, and we're going to fill that container. Absolutely fill it. That'll probably be enough. That's enough.
Thomas, you're not
That's
filling
enough.
it up.
Okay.
You're just putting it in that one to fill that one.
Okay. Very slowly pour until you think it's full. Everybody come look. You think that's full?
It says angle here, so it's
Okay. Okay. But you think it's full.
Yes.
So try pouring a little more water in it. Whoa, finally it went over. You think it's full now?
Yeah.
When you look at it, does it look like it's actually over full? Doesn't it? Okay? That's because water has this property called surface tension. And it will actually overfill a container because the water molecules are hanging on to each other with such tenacity. It's called hydrogen bonding. The oxygen from one end and the hydrogen from the other end, hydrogen plus, the oxygen negative, and they hold on to each other with ferocity. Okay. So we've got that full. Everybody agree, right? Now I want somebody, here's the scale. Let me get it away from me. And I want you to zero the scale. We're going to be doing what they say to do here. Procedure. Use a balance to find the mass of the basalt rock. I brought 4 pieces. Let's use them all. So someone put these, zero the scale first. Someone do that. Anybody, I don't care who. Everybody's going to do something. Once you get it in place, let's not be moving it. So zero the scale. You got it zeroed? Okay, put these 4 pieces on the top. Okay, read the scale. Someone else can help her, huh? 160 grams. Okay, so that's what you put on the back side. Mass of the salt, 160 grams. Okay? Now, we're not going to tie any strings. So if someone will pick up one of those pieces, anybody, there's 4 pieces there. Pick them up. 1 each. Okay? Okay? Some of you got 2. Somebody, hey, everybody gets involved here, okay? Okay. Now, very carefully, without getting your fingers wet, but lower this just as carefully as you can, but before your finger gets wet, release it very slowly into the water. We're going to catch the water with this, okay? Don't get your fingers wet. Lower it very slowly. Very slowly. Okay, good. All right, somebody else? All right. All right. Do this one especially very slowly and carefully. Good deal. All right. Now what we're going to do, what I'd like you to do is dump that water that's in that one completely out. Okay. Now, what we're going to do is take this container and pour it into that container. Okay? Now, with that container, pour into here. See, what we're doing now is measuring the volume of that rock. Because it's really hard to determine the volume. It was almost rectangular solids. Okay, someone read that and see how many, this is in milliliters, which is the same as cubic centimeters.
70.
70?
It's 70, it's 25, 50.
Oh yeah, probably like 6, 55, 60.
Each one of the little lines is 2 cubic centimeters, 2 milliliters.
Like 55.
Second?
53-ish. No. Yeah, about 55, 54.
Okay, all right. 55, and this goes on the back by volume, cubic centimeters. 55 cubic centimeters there. Okay, does someone have a calculator? Okay, take your mass and divide it by the volume and see what the density of that basalt is.
2.9.
Say again?
2.9.
2.9? 2.9 grams per cubic centimeter. Okay? Record that. All right. Someone else who hasn't done something, take this granite and zero your scale first, and then put the granite on the scale and measure the mass of the granite. Zero the scale first. Make sure it's zero.
Shouldn't it just go on?
No, those are fine. It's still at the surface, right?
Right.
Okay, there's room for it.
Oh, okay, I see what you do.
Okay? We did empty that bit yet. Okay, what's that one? Second? Is it 450? Yeah. From this angle, it doesn't look like it's over there at 450. There's 410, 20, 30, 40. Is it all the way over to 450?
No. Like 455, 45 something.
445? 445 grams. Oh, yeah, I'm saying this. I hope I can get it right. 445 grams of granite. Okay? So someone else, if you'll come pick up the piece of granite, I'll pick it up for now,
You want me to empty this?
and hold it by just a corner, and very slowly lower that into the container until just before your finger gets wet, and then release it very slowly.
You want me to empty this?
Yes, if you will, please. Not so. Very gentle. Oops. Oops. It's always gone in there before. Okay, what we'll do is turn it this way and drop it that way. Not drop it, but lower it very slowly that way.
Put it against the side,
Yeah.
so that way it doesn't.
Okay. I think we got it. Oh, okay. You answered that one, yeah. Okay. We had some spillage, so hopefully it won't be too bad. No, that's all right. Let's see what we got.
So it's 190 exactly.
190? 190 cubic centimeters. The
What
granite.
did you say for the weight?
Who measured the mass?
445, okay.
Okay, and with your calculator, divide the mass by the volume.
2.2.
Second,
2.2.
2.3?
Yeah.
Which was denser?
The salt.
The basalt. Were you guessing that to begin with?
No.
No, it looked like the
Because
granite
the-
was bigger and heavier and
Right.
everything else. But guess what? When you divide the mass by the velocity of the volume, you get the density. Okay. So sure enough, the basalt is denser. It has more iron in it. It makes sense for it to be denser. Okay? All right. Now what we're going to do now is very slowly lower this Okay. Now, let's turn to the questions at the front. 4 questions. You got 6 points now, everybody. So let's turn to the questions in the front. In what ways do igneous rock have different properties?
Ions.
Second?
Ions.
Okay, more or less iron content, there's one. Or you might say just mineral content or elemental content, something like that. Other ways they differ.
Density.
Density, we just measured that. Very good. How about others? Think of the lab you did, was it last time?
Different colors.
Different colors, okay, yeah, different colors. Okay. Anything? Second?
Size.
Okay. Well, yeah, anything would have different masses, but yeah, they certainly could. But density includes that. Okay.
Different makeups.
And what do you mean by that?
Like they're made up of different minerals.
Yeah, of different minerals. So different mineral composition. Part of that was in the different iron, but that's also a difference there. Okay. And what was one of the differences in the granite and basalt we were mentioning at the very beginning?
So interior something.
The what?
Like one was in the sea, in the
What?
water, and
Okay. All right. Where they were formed.
Yeah.
Okay. So in what way do they have different properties? Where and how they were formed, that might contribute to it. Actually, that might be better on 2, but we'll get down and say it again there. But what are some other ways? What was one difference between the granite and the basalt? Say again? Not the volume. We measured that, yeah.
The way they feel, right?
The what?
The way they feel. Texture.
Texture. What do we mean by that? What did you say?
I said the way they feel.
Felt. Okay, that's texture. Okay, right. Okay. And what would be the different textures? Coarse or fine. Okay. And what makes the difference there? Okay, now the weathering is breaking it down. This is the formation of it. What makes the coarse texture?
Water or where it's found.
Okay, now think of that. What was the difference between granite and basalt?
This
Looking
one's
at it.
rough. This one's smooth.
Okay, that's the texture. But what makes it that way? Turn to the side that hasn't been polished. Or just looking at that. No, that's wearing down.
The water rushing over it.
No, that's wearing it down. The what? You can see the individual
The crystal.
crystal size. Okay. The crystal size, that's another difference in property. What did you say?
It was in my head, but not on
Oh, I see. Okay. It got stuck in there somewhere. Okay. All right. So there are several ways that igneous rocks have different properties. Colors, texture, crystal size, composition. Wow, several. Number 2, explain the theoretical process or processes responsible for producing the different properties of igneous rock. Now, some of the same things we said can also be said here. What was the first of your...
more or less minerals.
Okay, yeah, the mineral composition. So that could depend on where it was formed. If it was formed deep in the earth, it's going to have more iron content. If it's formed closer to the surface at cooler temperatures, it would be less iron, more granitic. Okay, yeah, so you got that. That's a theoretical process. What was another thing you noted? Property. You wrote them down, didn't you? Texture. What creates a different texture? The large crystal size versus small crystal size. What determines that? The rate of cooling. Excellent. Okay. The large crystals were cooled.
Faster.
No, large crystal was cooled slower, making bigger crystals.
And then the
Small
smaller
crystals
ones
cool
faster.
very fast. So that would be. And that depends on how deep they were at the time of formation, right? So all these things have different processes. Y'all think you have enough there, or you need a little more? Ah, that's good. Okay, y'all are really kind. Okay. I'll let you finish writing, though. I'm trying to say all this so that the people at home can hear it, too. I know Bertram has to work today, so he's going to try to listen to this and get it. Okay. Now, number 3. According to the experimental evidence of this investigation, the measurements you took and the calculations you made, propose an explanation for the observation that the bulk of the Earth's continents are granite, but the basalt are found mostly underneath the sea. Why would that be the case? Based on what you discovered today in your measurements and calculations. The lower density would tend to rise. The denser would tend to subduct underneath. So that pushes up the granite into continental crust, and the oceanic crust basically stays low and actually goes under the other. Does that make sense? So the denser materials go deeper, the less dense material kind of floats on the other. Okay. The denser basalt would be in the bottom of the ocean, or maybe even subducting under the continental crust, whereas the lighter density continental crust would rise above. The granites on the continental crust, it would rise above the basalts. Okay, number 4, I'll let you answer however you want to. If there's no answer there, there's no points there, but give some type of answer. More than a yes or no, but not a whole lot more, okay? As much as you want to say there. And when you get that done, there's your 10 points. That's all we got in the lab today. So the next 15 points or more, you can get, if you did miss something or leave something out, you can get, I want you to get at least 25 points worth of credit. Those come from the questions, okay? Any questions you have now on the lab? Did you understand those questions we answered there? If there's no questions, I can go and shut down the recording. Any more questions? Okay. If not, I'm going to shut it down.